Welcome everybody. Thanks for joining us for installment of the Dream Seminar. It's a real pleasure today to welcome back to Berkeley one of our graduates, Professor Cathy Wu. Cathy graduated from EECS at Berkeley in 2018, and she's a professor. She's an assistant professor at MIT. Where she's jointly appointed between civil and environmental engineering and IDSS, which is the MIT Institute for Data Systems and Society.
That's right.
Data Systems and well, it's kind of like ours, CDSS, IDSS. So I think I was sort of systems, data systems. Okay. And also within LIDS, the Laboratory for Information and Decision Systems. And her lab, if you look at the students that work with her in her group, they're kind of distributed among those different institutes fairly evenly. So she brings kind of a diversity of student backgrounds into her work. And I think you'll see that in the work that she's presenting. So today she's going to talk about research that her lab does in what's called sustainable roadways. Really thinking about this combination of how to bring learning methods and control and decision-making together to think about not just autonomy in not just autonomous cars, but really how we can think about taking the current system with human-driven human interaction and bringing in autonomy in a sustainable way. Her lab focuses on learning, optimization, control, modeling, and their application to these emerging mobility systems. She's won a number of awards, including the NSF Career Award, and she's got a whole lot of cool press. So Nova, Wired, Science, and TEDx at MIT are just some of the things you'll find if you Google Cathy and you look at some of the cool stuff she's doing. So welcome, Cathy. It's a pleasure to see you again here.
Thanks so much, Claire, for the very warm welcome. Yeah, I love being back here. It actually feels really crazy to me to just walk around again. Really love it. So I also learned today that there was a recent memorial service for our late Professor Praveen Varaya, which I unfortunately was not here for. So I think it's only best to only right to dedicate this talk to him. Because this is really in the tradition of intelligent transportation systems and how we can improve systems that touch our lives every day using control and optimization. Yeah, so I'm excited to be sharing some of what I've been working on over the last 4 or 5 years, which is titled Intelligent Coordination for Sustainable Roadways, with a slightly provocative question of if autonomous vehicles are the answer, then what is the question? So before jumping in, I'd like to just start by saying that I feel really fortunate these days to have found some problems that I feel really excited about every morning to work on. And for me, what I think that means is problems that have the potential to leverage emerging technology, improve people's lives, but at the same time, they are interesting technical problems. So this sort of intersection of this space, and this maps pretty well to the sort of technical communities that I engage with, which are roadway autonomy, thinking about sort of the autonomous systems for roadways, looking at intelligent transportation systems and all of the value that it brings us, as well as learning for decisions and control. So this talk is about roadways sort of as a system. It's really easy to take these for granted. We use these sort of every day, but they are the circulatory system of the economy. In fact, we rely on these. They link producers to markets, workers to jobs, students to schools, and sick to hospitals. They really link up the country, but they are not perfect. They are far from it. And so one approach that we've been taking to improve roadways for, say, the last 20 years has been this, what we might call autonomy-driven design. This is the idea that if we can achieve autonomy, then vast societal benefits will be unlocked. So the reasoning goes something like this. Let's figure out perception, planning, common sense reasoning, social orientation, altruism, a few other components. And then after we have those, then we can use that to achieve more sustainable roadways. I'm going to restrict the definition. It means a lot of things. Here I'm going to talk about sustainable roadways as safer, cheaper, cleaner mobility. As you all may be able to tell, this has been harder than we thought. Roadway autonomy has gone through this sort of hype cycle. I'm sure many of you have seen this before. This is the Gartner hype curve. It describes the life cycle of a technology, including the sort of peak of inflated expectations. So let me recap this wave of interest in roadway autonomy. It's not the first, it may not be the last, but this sort of kicked off in about 2005 with the DARPA Grand Challenge, followed by the Urban Challenge, which really got industry interested in this space. And so then we have sort of every big tech company, every OEM sort of working in this space. So a few years later, I guess a decade later, we have articles that look like this. Wide adoption of self-driving cars could be only 5 years away. This is Business Insider. Followed shortly after by the unfortunate crash of the Uber self-driving vehicle, which actually killed a pedestrian. This sort of I don't know if it's causal or anything, but this sort of coincides with the sort of diminished expectations for this technology. And now we are, somewhere there in what's called the trough of disillusionment. So this is sort of where we are now. I want to revisit actually the rationale for roadway autonomy because it does have its merits. So the first motivation is safety. We have 43,000 fatalities on US roadways. This is the number from year 2021. And there's a very famous study from NHTSA, which concludes that human error is involved in about 94% of these fatal crashes. So this is a really large number of deaths. It's like one of the leading causes of death of young people as well. Yes.
94%.
Yeah.
Is the methodology there something where
I'm very careful with the wording here. Yeah. So the wording is not that humans caused the fatality or anything. There are a lot of causes, but human error is involved. So the way that NHTSA's methodology describes this is that the human is the last link in a causal chain. Does that answer your question?
It's saying that from their perspective, the human has done something differently.
Yeah.
That wouldn't happen. That's what makes it.
Yeah. Yeah. And there could be many causes in that causal chain, but this was the last one that made the critical decision that led to the fatality. And so this is often misquoted. So I'm trying to be a little bit careful here, but this is often this is the same statistic that is used by autonomous driving companies, sometimes misquoted. But regardless, human error is involved in 94% of crashes, according to this famous study. And it is therefore very challenging to conceive an approach that would get us to 0 deaths, this vision 0, if we don't remove the human from the equation. Okay, so right now I'm just recapping the sort of motivation. The other is cost. So travel time by far is the largest component of the overall economic cost of moving like goods and people throughout the US. This includes the literal time spent, but it also includes the time that we spend driving rather than doing something else. Okay, so multiple studies basically say that Americans spend about an hour on the roads each day. So I don't know about you, I could use a 25th hour of the day, and that would be, immense economic value. We could do this, we could all hire like taxi drivers, but the issue there is cost. Okay, so autonomy is seen as a way to actually drive that cost down. there are many more motivations. One that I'm going to touch on is the environment. We urgently right now need to decarbonize transportation. One element of that is electrification. Transportation is right now the largest contributing sector to greenhouse gas emissions in the US at 29%, and a vast majority of these are on roadways. So one motivation was that, or is that autonomous vehicles could, help optimize traffic flow and thus emissions as well. Okay. It actually has like even more applications. It could include sort of sharing of vehicles, de-emphasizing performance, platooning, vehicle right sizing. So there are a lot of connections, even accelerating electrification. Okay, so this autonomy-driven design was harder than we thought. And so on a scale from not very sustainable to very sustainable, we've had a lot of aspirations of autonomy being sustainable. This includes my own work on mixed autonomy traffic. It is sort of like most of the work that is considering sustainability through the use of autonomy. What I was trying to do with mixed autonomy traffic is say like, okay, a lot of work considers like all the vehicles are autonomous. Let's like tend towards more realistic systems by saying only a fraction of vehicles need to be autonomous. But even that is making a sort of strong assumption now that we can get, any autonomous vehicles to work. And so at the same time, our current sort of like level 5 autonomous vehicle prototypes have yet to, actually make our roadways cheaper, safer, or cleaner. So I think that the issue here is that the technology readiness of autonomous vehicles is quite low. So achieving this idea of sustainable roadways, I think, requires a different approach. So for lack of a better name, let's consider what we might call use-driven design. So what this says is, let's consider why we want to improve roadways first, and then let's design for that. So here I make this observation that we're sort of claiming, based on the previous few slides, that autonomy is sufficient for sustainable roadways, but is it necessary? To understand what's necessary, we can study potentially relaxed notions of autonomy. Here's the x-axis here, ranging from all the way from what we have today in terms of the status quo, all the way to fully autonomous agents, which we have been hoping would happen. So use-driven design is about understanding this space in the middle here. How sustainable of roadways can we actually achieve with relaxed notions? This space is not completely empty, and I do take a lot of inspiration with a few notable areas like connected vehicles, adaptive cruise control, ADAS, automated highway systems. But I would say most of the work right now is sort of on the far end. And unfortunately, this is not trivial because it's not even clear how to label these axes. Like, there's no like linear spectrum between status quo and like fully autonomous systems. It's not clear. Like, sustainability has a bunch of metrics. Like, what do we care about more or less? And what does technology readiness even mean? So this talk is not going to like fill in this space by any means. It's going to talk about one specific relaxed notion of autonomy. And in particular, I'm going to talk about coordination of vehicles. So we can think of this as like something that we can do as a result of autonomy, but maybe it doesn't require all the pieces of autonomy. So it might require some planning, some altruism, but it may not require sort of every component. And we can then start to ask, like, okay, if we could coordinate vehicles, to what extent can it lead us to more like to safer, cheaper, cleaner mobility? And that tells us to what extent, autonomy in its full form is necessary. Okay, so this is the outline for the rest of the talk. We're going to consider these one at a time. How can intelligent coordination make safer roadways, cheaper roadways, cleaner roadways? As a bonus, time permitting, I think I probably won't have time, but I'm always optimistic. I'm going to talk about how these problems of intelligent coordination are also like annoyingly hard to solve, and how we might go about designing new methods that are more effective. Okay, so the first the first piece here is on safety. I'm going to discuss work that was recently published in the Transactions on Robotics, which was done with my two students, Cam and Siri. So this safer problem challenge, simply stated, is that safer human drivers are actually incredibly safe. The bar is really high. So according to national statistics, we have about one fatality every 80 million miles. That is a big number. For comparison, Waymo over the last 10 years has driven about 20 million miles total, just total. So the estimates are that Waymo would need to drive at least 10 times as many miles, maybe 20, maybe 30 times, without fatality to provide confidence that this technology is as safe as humans. Okay, so let me put this into perspective some more. This puts humans actually at around 8 nines of reliability. This is 8 nines after a decimal point. What this means is probability without failure. Okay, this is like very high. For comparison, I use like AWS Web Services is at around 2 nines of reliability. My Roomba is at around 1 9 of reliability. Air traffic control, though, is awesome, is at around 10 nines of reliability. So on the other hand, the best estimates for autonomous driving right now is anywhere from like 2 to 4 orders of magnitude below human driving reliability. Usually there is often a trade-off between cost and reliability. So now we add the x-axis, which is cost of sort of achieving this level of reliability. And there are some sort of naive solutions. So we can make this safe by like building dedicated infrastructure, but it's sort of understood that this is exceedingly expensive, so we don't want to do that. So most work these days, I would say, sort of like works from where we are and tries to improve the reliability or the cost. I think like I don't do a lot of the work in this space, but I think that we need some breakthroughs in order to sort of close the orders of magnitude gap here. So this work is going to take a different approach. We're going to start with something that's safe enough, humans. We're going to bring in ideas from something that's even safer, air traffic control, and we're going to try to improve on the reliability and or cost, okay, because of this existence of a trade-off. Okay, so the inspiration is air traffic control. The idea is to bring air traffic control, which is in like open space, to dense roadway traffic. The idea is to complement autonomous capabilities, which may be limited, may not be perfect, may not be as reliable, with remote supervision from expert operators. And the question is like, how do we quantify this trade-off then between reliability and cost? In particular, we sort of like to call this problem sort of the scalability of supervision. As the fleet size grows for autonomous vehicles, how many operators are needed to provide a certain level of assurance on this problem? And just keep in mind for this talk that the status quo is 1 operator for 1 vehicle, whether it's like autonomous or not. So we analyze this scalability of supervision using a queuing model. So the arrivals to this queuing system are risky events. They are served by or supervised by these remote operators. You could really think of this as like a call center with like steering wheels, potentially. So we are interested in essentially the probability that there is a risky event that arrives and all the operators are busy. Okay, so this is modeled as a queuing system with no buffer. So the capacity is equal to the number of servers. And we're interested in the probability of what's called service loss, which is the probability that we cannot guarantee service. The probability that the system has risky events at the same time. And so then we have a measure of reliability, which is 1 minus this probability. Okay, so the specific problem setup that we're going to consider to keep things simple is we're going to model highway merges. So here's a highway, it's a circle, and here's a merge. We're going to only consider merges. So anytime that there could be a conflict, we're going to flag it. We're going to be very conservative. We're going to flag an operator. So keep in mind, you don't always need a supervisor at all times. If the car is not gonna like doesn't have any risk of impacting another vehicle, then we don't need an operator. We're using sort of worst case, very conservative reachability analysis to determine when there could be a potential conflict. If there is a potential conflict within the amount of time that an operator would need to take over, then we invoke an operator. We are interested in how many supervisors are required to achieve a certain level of reliability and how that changes as the number of autonomous vehicles or the adoption rate grows. Okay, so what happens when the AV adoption rate grows? I'm going to discuss this in two parts. I'm going to spare you the details. I'm just going to try to provide you with some intuition. So first of all, more autonomous vehicles implies that there are more AVs to supervise because there's going to be more vehicles trying to merge. Okay, so you can imagine that, so here's sort of some numerics. As the AV adoption grows, which is the x-axis, for a fixed number of operators, which is each shaded region. So this, imagine like this curve right here is for a fixed number of operators. The y-axis is reliability. So as there are more vehicles, more AVs, the reliability will drop for this fixed number of operators. And then we can, adjust that based on the number of operators. However, at the same time, more AVs, say, for instance, on the highway, can provide more information that can reduce when operators are needed. So then we have this like curve that goes back up when much of the system is autonomous. The system is sort of more or less fully observed, fully predictable, and so on. And so we have some nice curve like this. So this is actually can be characterized very nicely using more or less a direct application of standard results from queuing theory. A little bit more interesting is this second piece, which is that another thing that more AVs implies is that there are more AVs that can potentially influence traffic. What this does is it can potentially influence whether or not there is conflict at merge points, okay? Potentially by blocking, slowing, et cetera, other vehicles. So the key insight here is that an ounce of prevention is worth a pound of cure. So if you can prevent the need for supervision in the first place, that goes a really long way. So this does turn out to have a huge effect on reliability. So without coordination versus with coordination, the curves are basically just dramatically shifted up, okay, for the same number of operators. So comparing this color actually with this color. Okay, so the analysis of this actually boils down to like computing the probability that the nearest vehicle to the merge point is an AV. So the use of order statistics. So to give a numerical example, this I found really informative. So we can basically plug in some reasonable, hopefully, numbers. 15 seconds to monitor a merge, and sort of some values for peak travel time for a few on-ramps. We can compare what happens with and without cooperation. And this is a specific example, just looking at sort of this 30% adoption. So under AV cooperation, this operator team can actually cover 8 nines of reliability, while without cooperation, it's more at 99%, okay, 2 nines. So this is actually a difference of like 6 orders of magnitude in terms of reliability. Ultimately, this translates to about 42 vehicles per operator, and recall that the status quo is 1, okay, 1 vehicle per operator. Okay, so this is all I want to say about this work. The key idea here is that remote supervision and coordination of vehicles can substantially improve the system reliability and or the cost, because you can trade off the two. This, we believe, is the first queuing theoretic model for this combination of supervision and coordination of AVs. And I hope that this starts to convey that relaxing this notion of autonomy into, allowing some components to not be fully autonomous opens up a richer design space.
Question: whenever you talk about nines, these tend to be pretty dependent on assumptions of independence or stochastic, some kind of stochastic model.
Yeah, yeah, that's fair.
So what are the kinds of assumptions that are driving that.
I see.
You're not getting that with Chevy, right? You're getting that using,
Hold on.
yeah.
Yeah, I'll have to think about that. I think that there are a few assumptions that I have been thinking about, but I'm not sure it gets at what you're talking about. So for instance, this reliability needs to be multiplied by the reliability of communication infrastructure that is needed to implement this kind of thing. And the reliability of like then the human being like not having a stroke in the call center and whatnot. So I think there are a few factors that are missing here that need to be incorporated. I don't think it's that kind of reliability that you're mentioning here, but I think that's a really interesting point that I will think about.
Yeah, I mean, this is a related question. Take offline, but like, do we need to assume, for instance, that like, different cars are going to fail independently? Like, if it was just like suddenly foggy and some reason and all of that in trouble, is this a problem? Or?
So I think that's super, super interesting. I wonder if there's a way to make the framework more adaptive to factor that in and like scale operators up and down and whatnot accordingly. Yeah, so I think that's really interesting. Okay, so I want to move to the next piece, which is on cheaper, on intelligent coordination for cheaper roadways. We touched a bit on cost, but I want to take cost very far in this direction. So this is joint work with my students, Junghoon, Siri, Mary, and also my collaborator, Roy Dong, also a Berkeley alum at UIUC. So in the interest of time, I'm going to mostly focus on the average case performance analysis, but I'll mention the work on worst case stability. So a much cheaper way to coordinate vehicles is to just give drivers an app. Okay, so if you put this in the context of the SAE levels of autonomy ranging from 0, fully autonomous, fully manually driven vehicles all the way to fully autonomous driving, this is what we might call like level 0.5. So this is possibly the lowest cost and nearest term form of autonomy. So what we have learned in the past, both from our own work and others, is that fully autonomous vehicles are able to do good things for the system, even if like only a fraction of vehicles are autonomous. It boosts performance in terms of throughput, speed, and whatnot. So we know that level 5 is sufficient in this way. And now we want to know if it's necessary. So what we can do is we can sort of, I don't know, do a binary search or something, but I'm just going to be more interested in like this endpoint. If this endpoint can already do this, then, then that was not necessary. Okay, so this leads us to the problem, which we call human compatible driving. And the research question is, to what extent can guided human drivers achieve the traffic optimizing behavior of autonomous vehicles? So the goal here is to design these human compatible control laws, by which we mean that they are implementable by human drivers. Things can get very complicated, but we're going to take a very simple model. So we're going to say that we're going to consider just coarse grain driving guidance. Okay, so AVs can follow instructions very precisely, like every, like 10 hertz, and human drivers can follow instructions, at a much lower frequency. So let's model this very simply using piecewise constant guidance. This is also known as zero order hold, where an instruction is held for some delta amount of time. And we can, vary this value. So we actually have a linear spectrum from AV to human somewhere. Also, you can think of the guidance as some kind of like dynamic speed limit or dynamic acceleration limit. It's not exactly what the human needs to follow. It's, a limit. So the human still can maintain safety and things like that. So the research question is, how coarse of guidance, so sort of this like hold length delta, can still achieve this traffic optimizing behavior. Okay, so to be more precise, we're going to have a traffic scenario where a fraction of vehicles are row are guided and a fraction 1 minus row are unguided. The guided vehicles are going to have some kind of control law that is updated every delta steps, whereas the unguided vehicles will follow some kind of conventional driving model. We're going to consider a variety of traffic scenarios. So every combination here of driving guidance type, the hold length, and the traffic scenario yields sort of a different multi-agent control problem. we're going to take two approaches. One is we're going to learn these human compatible control laws using deep reinforcement learning, sort of just independently to start. And then we're going to also analyze the stability of the coarse grain system, which unfortunately I don't have too much time to discuss. So the first thing that we want to talk about is this ring network. It's like the cart pole, like the very simple system in traffic, and it's, I think, interesting for a couple reasons. So one is from a theory standpoint, this coarse grain guidance actually coincides with this like older piece of work called sample data systems. So we can actually leverage some work that's already been used to analyze the stability of these systems. And we can actually do that for this kind of more simple traffic system. And we can derive the sufficient conditions for system stability. Okay, from the empirical standpoint, this is sort of an easy problem in that there actually is an optimal solution that is just a fixed velocity. Okay, so we know that it is solvable. So if we apply RL to it, we know what to expect. So here, this is really hinting at a new direction of work that I'm now very engaged in, which is the brittleness of vanilla application of RL. So let's take a look at the plot here, and in particular, the red line. Okay, so this is the y-axis is the average speed. We want it to be high. The x-axis is the hold length. So this right here, the very small, very fine hold length. This is our model of an AV, and we would expect the performance to degrade a bit. In this case, there's a fixed velocity that is optimal, so it's a trivial problem from some standpoint. We should be able to do this regardless of the hold length. Now, if we train this for with RL, there is there's even though these problems are actually almost identical to one another, this is training 5 models, doing our hyperparameter tuning, lots of stuff, we get something like this. This is unacceptable, I think, for use of deep RL. So this actually motivated us to develop a method which we're calling the temporal transfer method. So it is really leveraging this idea, these are basically all the same problem. They're not exactly the same, and we have to keep that in mind. So so the idea here is consider some target hold length. So this is a problem that we want to solve. The intuition here is that the coarser the problem, the easier it is to solve because there are fewer decisions to get right. Okay, the effective horizon is shorter. The finer problems provide, however, they sort of upper bound the performance. Okay, so we can think of the coarser problems as having less variance in training, and but having potentially greater bias, because if we sort of train something here and then we transfer, it may not do so well because it was limited to begin with. So there's sort of a sweet spot in terms of identifying an ideal source task that to train and then to sort of transfer such that it's sort of easier to train, but can sort of balance this bias and variance. Okay, and then we can basically solve this using a stochastic form of binary search. So by doing something like this, we are able to smooth out the previous system into sort of the flat result that we expect, and also for more complex systems where the red is sort of the training curve using vanilla RL, and then the blue curve is the sort of result from the algorithm. Okay, so now this is all I want to say about that. I should say, so what we see here is that as we increase the hold length, we do see a performance degradation, which is what we would expect. But we also see that this still outperforms sort of not doing anything, which is the green line. Okay, and this region right here, this sort of 8 seconds is from human factors literature on sort of what's considered human compatible. We're sort of starting our own user studies in collaboration to determine what that is for these scenarios here. But suffice to say that there is some kind of very small degradation, and there is still improvement. There is still this human compatible guidance can still preserve benefits from autonomous vehicles in terms of speed, in terms of throughput, in terms of fuel across a variety of scenarios. So the implication is that these guided human drivers could enable low-cost near-term autonomy benefits. that vanilla deep RL is unfortunately brittle to even minuscule changes in the environment, and that this temporal transfer method could improve the reliability of learning these human compatible control laws. Okay, so moving on to cleaner. This is probably the largest project I've undertaken. It's still ongoing. This is sort of split roughly into modeling pieces and control pieces. This is recall the motivation that we urgently need to decarbonize transportation. This is something that I sort of found really helpful when I was designing this problem. It's the back of the envelope calculation. Let me sort of tell you first. The opportunity is like intuitively, traffic signals basically induce stop and go traffic all the time, everywhere. It's about 50% of vehicle miles traveled by my back of the envelope calculation that are near these signalized intersections. And according to a recent survey, if I take this is a very rough meta-analysis, I took all the studies and I computed the ±1 standard deviation in terms of how much emissions fuel could be mitigated by control of vehicles, coordination of vehicles, and it's something like 6 to 28%. This means if we're optimistic, up to about 15% of emissions is just wasted. Like fuel is just wasted. It's not doing anything. It's not improving anyone's quality of life. We could just potentially get rid of it. So to show in graphic form, so this is sort of an intersection with fixed time control. And you can see like plenty of queuing occurring. And here is sort of a model of what happens with eco-driving. The vehicles are provided with some speed guidance such that when they get to the light, it is green. So the question here is, would coordinating vehicles to reduce CO2 emissions at intersections move the needle on climate change mitigation goals? There is a vast literature on this. This is called eco-driving at signalized intersections. There are dozens of studies, but we don't see any of it sort of in practice. And so I was really curious, like, why not? And so the goal here is not to investigate how to do eco-driving, which is the focus of a lot of these studies, but rather on should we? Like, does it move the needle? Is it worth it? So for this, what we want to do is we basically want to compute the expected improvement of eco-driving across possible driving scenarios that would occur, over the course of a city, over the course of a year. I'll mention that this is already known as like sort of a good idea for highways, but for intersections, it's sort of more complicated. So the central challenge, I would say, is that there is basically coming from the diversity of intersection scenarios. We can look at this in picture form. So here's an intersection. So this is Salt Lake City, our partner for this research project with the Utah Department of Transportation. So intersection has a number of attributes, say, for instance, the number of approaches, the number of lanes in each approach, and the number of turning lanes, the turning restrictions. So if you just look at those sort of like three attributes, if you look at different intersections, you have different attributes. These are attributes that clearly affect the performance of eco-driving, so we have to analyze these as sort of different control problems as well. So these are also only some of the factors that affect eco-driving, namely the topology and the turning restrictions. Obviously, the slope or the grade of the road affects eco-driving, the weather conditions, the travel demand, the vehicle types and age. So all of this sort of affects the performance of eco-driving. So we want the expectation recall over these sort of control problems, and there are a lot of them. So the challenge is that eco-driving controller design has focused on specific settings, again, on how to, not should we. And so there's no known approach that can simultaneously handle like a lot of these considerations. There's also no known approach that scales to analyzing sort of millions of scenarios. And so the approach that we're going to take is one of multitask reinforcement, deep reinforcement learning. The second challenge is really unfortunate. Large-scale modeling, at least that's available to academic researchers of traffic, has really focused on highways. And so we have to sort of model the urban aspects as well as the eco-driving factors. So we basically engaged in a very large-scale modeling project. We are modeling 10 US cities selected based on data availability, as well as high-emitting regions, which always happen to be cities. We ended up with around 30,000 signalized intersections, and these are sort of different attributes like the lane length, speed limits, turning lane configurations. It turns out that in order to do this at scale, we want to use open data like OpenStreetMaps. What's unfortunate is that, like, unfortunately, most of the attributes are missing. So we had to develop a data imputation pipeline to fill in a lot of these missing values, figure out how to validate that, and so on. So that's one part of the modeling, but we also care about the living thing that is the intersection, the things that are non-static factors. So this is, for instance, the weather, the temperature at different different seasons, the traffic flow at peak and sort of off peak. So this leads us to something like 1.5 million scenarios that we need to model just to analyze sort of 10 cities. To give you a sense of scale, this is about 10% of the country. In terms of signalized intersections, there are about 300,000 total. So this is unfortunately not everything. So here is like a really messy diagram of our overall modeling effort. And here I have just highlighted the static factors. I'm not going to be able to go through this in all of its detail, but one thing I want to highlight is that what really helped allow us to do this work is that many of these factors are actually captured by an industry standard model from the EPA, from the Environmental Protection Agency. This model is called MOVES. It's a very, very rich emissions model that captures, for instance, the age of the vehicle, how it operates under different road conditions and temperature, humidity, and all this. It's a very sort of sophisticated piece of software. Unfortunately, if we used it naively to compute our estimates for like 1.9 million or 1.5 million scenarios, we computed that it would take something like 9 years. And this is not even talking about using it for optimization. This is just using it for evaluation. So our solution was to reverse engineer it and then basically learn neural network models as surrogates in place of these models. And so that has helped us actually do this project. Okay, so for the actual eco-driving analysis, we are modeling just the acceleration of the vehicle. So we could potentially do even better with lane changing, but the problem is sort of large enough as it is. So let's keep it contained. And then we're basically like the general approach is like, okay, first let's consider multitask reinforcement learning. This is sort of standard. You can consider every traffic scenario variation to be a task, and then every rollout that is sampled during training is a traffic scenario variation sampled at random. We're doing sort of very standard training practices using the PPO algorithm with ActorCritic. This is a multi-agent problem, so we're doing shared parameter multi-agent following the centralized training and decentralized execution paradigm. The reward function, we extend some of our prior work on reward function design for eco-driving. And unfortunately, this works, but like not quite as well as we need it to. So we do a very small innovation, which we call multitask reinforcement learning. And it's very reasonable if you think about it, that a single policy would not be able to do very well on like 1.5 million different scenarios. So we simply partition the space into a small number. And basically the idea is let's learn a small number of policies to sort of be effective over the 1.5 million scenarios. So here we choose something like 7. Okay, so it's still much smaller. And this can be partitioned. We choose a partition based on the number of lanes and the number of traffic light phases. Okay, so this is heuristically determined. And then to assemble the final set of control laws, even though we sort of trained specific policies for different environments, we can still apply all the policies to all the environments to see to use the most effective one. So we basically select the control law that maximizes the effectiveness. Okay, so what do we find in the end? This is our result for Salt Lake City. We're still crunching the numbers on the other 9 cities. So we generally see sort of, okay, as we increase adoption of guided vehicles, there's more benefit, which is clear. But does this move the needle? So our estimate right now is that at 100% eco-driving, this yields about 11% fuel reduction. if we scale this sort of naively, so if we assume that this city is representative of the country, we scale this to the country, we see about 2% reduction in US-wide CO2, not just for transportation. And I've tried really hard to understand, like, what's the needle? Where's the needle? How big is it? And what does it mean to move it? And so one gold standard that I have is that a 1% reduction in global greenhouse gas emissions is sort of considered the gold standard, according to the venture fund led by Bill Gates. Okay, so this is in that ballpark. We can also see what happens when we have partial adoption. So around 20% of adoption gives us about a 0.4% reduction. So 20% adoption gives us about 28% of the benefit. So there's some nonlinear gains there. Okay, so in short, eco-driving as signalized intersections, I think, could substantially contribute to transportation decarbonization. As part of this work, we did extensive modeling of urban traffic for 10 major US cities, which fills a gap in traffic modeling beyond highways. We devised these neural surrogates of the industry standard emission models, and that this multitask reinforcement learning actually enables us to tractably analyze over 1 million eco-driving scenarios. Okay, so I don't think I really have time for this last piece, so I think I'll keep this very brief. As you can see, there's some brittleness that arose as I sort of went through the previous parts, and we see this over and over again, and like in a lot of work that I'm not talking about here. So the question is sort of, you know, we sort of went back and asked ourselves, like, is it just us? Are we just bad at using reinforcement learning, or, you know, is there something sort of deeper here? And so we found that it's not just us. We found evidence of brittleness of deep RL in existing benchmarks. So first, we looked at one that's close to home. This is traffic signal control, which is control of traffic signals, not cars. But there is a benchmark here, and we basically took the same models of intersections that we devised for the eco-driving, and we basically applied existing traffic signal methods to this new distribution of traffic intersections. And what we find is that if you compare traditional control methods with deep RL methods, the benchmark reports that like the deep methods do better than fixed time control, which is what's deployed out in the streets. But if we evaluate it under our this actual distribution from Salt Lake City, the classical methods actually do better than RL. Okay. Yes.
Are you fine-tuning on the new data set?
Yes. We're fine-tuning. We're training on this. We're training on this set. It's not a generalization problem. It's an algorithmic robustness problem. Yeah. And so we actually find this to be true also for classic sort of standard benchmarks. And so this is really unfortunate. Okay, so then we basically have started this like line of work, basically saying like, okay, well, pure learning methods don't seem to be able to do anything, or like not reliably enough. But at the same time, these learning methods are motivated by how rigid model-based methods are. So how do we reconcile these two? So can we get the best of both worlds? Can we leverage the problem structure as in model-based, but yet provide the flexibility of for like the difficult to model aspects? And so here we have this new line of work on sort of learning-based meta methods. And I'll just close on this slide. We it's hard to do this with control right now because you don't have like an existing like benchmark data sets and whatnot. But it happens to be that discrete optimization has decades of experience sort of with natural variations of problems that like have both there are existing methods that leverage the problem structure, but there's still room to improve. And so, for instance, we've done some work on like the vehicle routing problem. Over 60 years, there's been a lot of study, and a lot of variations of the vehicle routing problem have been uncovered and studied. But yet there's still room to improve these methods. So we're sort of saying like, let's treat this as a data set. Let's pretend a lot of these don't exist yet. And let's design some algorithms for one and see if they're going to be like actually robust to the others. Okay. So that is my talk. And I hope you take away that autonomy is sufficient, but it may not be necessary to make substantial progress on sustainable roadways. And that this idea of use-driven design, actually allows us to make substantial progress, and that there are many interesting problems in this space. So thank you very much.
Okay, let's thank Professor Cathy for her wonderful talk. I think here's the Q&A section.
Yeah, so the kind of coordinate control stuff, that was really cool. I had a follow-up question about it. So you were talking about how you can kind of just, learn on the course thing and then just use that for the binding. Have you thought about instead using that more as sort of like a regularizer or the distance initialization where, I can start from there, but then actually try to make use of the, more fine-grained stuff?
Like more as like a curriculum, like gradually relax the,
curriculum.
Yeah, we have thought about it. I think that it's conceptually clean to explain it this way. In practice, I think some of those ideas I think would be very natural. Yeah, because I think it is like a more fluid version of like what we're describing.
First of all, thank you for your presentation. I thought it was very interesting, and I have to applaud your focus on mixed traffic situations and a focus more on infrastructural systems as opposed to vehicle systems. But I have a question concerning essentially this idea of coordination runs mixed traffic. In a way, it's assuming that mixed traffic is solely made up of automobiles. And I was wondering if you thought about how would you incorporate a model, or how would you incorporate into the model non-automotive model?
Yeah.
So bicycling, pedestrians. Ford has released a patent for an app for pedestrians to basically coordinate between Ford AVs and pedestrians. And I was wondering if you have any insight on how you would approach those types of situations.
Yeah, that's a really, really good question. And yeah, I'll admit I spend most of my time thinking about coordinating cars with cars or cars with infrastructure. I am starting a small effort on like coordinating in the presence of pedestrians. So not coordinating pedestrians, but like I think from my standpoint, I think what I can contribute to the conversation is more like in the presence of pedestrians, if they do what they do, how does it decrease the effectiveness? So how can we be more realistic about the estimates that we're making here? I think that's something that we really need to do for like in this line of work. And I think the points that you raise are really good.
Thank you very much.
Yep.
The course and the fine policy, like from my perspective, relates to the sample data and the sample theories, as you mentioned. But I'm mainly wondering, like, what is the distinctive feature of the like systems that you apply this framework, like compared to the more like classic like sample data theory?
Oh yeah, so I don't know if this is just an artifact of how like control systems developed. So I don't know if this is like a deep difference. But sample data systems typically are for like it actually evolved in the age of like digitizing electronics. So it used to be that you would just do analog control, and then at some point you had a clock, and at some point your control actually became discretized, okay, because of digital electronics. And so there is this field that tried to understand like if we did continuous control before and now it's discretized, and there is like some zero order hold for like very, very small but existent like durations, what are the stability implications? So the difference between that and what we're doing is like that would be like, I don't know, milliseconds or in terms of the delta hold length. And here we're talking about seconds or tens of seconds or even more. Yeah.
So you think that the time scale is
I think the time scale is different, but I mean the framework applies. Like it's just a scaling factor in terms of the analysis, but potentially in terms of the implications of that analysis, that may be different as a result of the application. Yeah.
I'm curious about the reason behind, for example, like say ES your case study, Why
They
that?
they were willing to work with us. That was the top qualification. They actually are one of the leading, if not the leading, traffic signal management systems in the country. So they're very well retrofitted. They have like very high quality equipment. Their data is available. There's some additional data that we need that they are also able and willing to provide. They've been wonderful partners. Yeah.
You mentioned in the launch that you mostly focus on roadway like transportation system, but I'm kind of interested in like air mobility system, like where we don't have this kind of infrastructure as well as like the vehicle system. So like, do you have insights on like whether kind of your approaches would be kind of transferable to these other types of mobility systems?
Yeah, I am not sure about like the first three parts. I think that we're finding like quite a bit of application as we're developing new algorithms. So here we're looking at vehicle routing problems. We're looking at automated warehouses in collaboration with Amazon. We're looking at mixed integer program solvers and all of the applications of that. And so I think this is like a pretty rich space. I think that I really focus here on like really thinking about roadways. So I think it'll require like a brainstorm or something to think about applications elsewhere, because there's so much structure in the problem here. Yeah.
I want to know a little bit more about, like, to be more specific about like the variations. You have the diagram about like using the RL versus.
This one?
Yes, yes. I wonder what caused the RL to perform worse in the natural variation case. Is that like the out of the distributed range?
Yeah, I tried to at least see if there were some outlier cases that was like causing RL to fail and then skewing the statistics, but it seems like RL is failing sort of across the board as we like sort of clustered based on the attributes of the intersections. Like we couldn't find any patterns. So I think it will require a deeper analysis of like, is it really this distribution or is it the algorithm? Does that answer your question?
So okay, so the variation of the testing data is like it's different from
No, this is the training data.
oh, this is
Yeah, we're training and testing on the same thing. To be fair to prior work, like we just have new intersection configurations. The difference between this and the previous work is just different lane counts, different speeds, speed limits, different like lengths of the roads, different like inflows and whatnot. But we're taking the same algorithms and we're training them on each individual scenario, not even multitask, just applying RL on each individual one. The limitation that I am aware of that is informing our next work is that we did not hyperparameter tune for every single scenario. Okay, so we use the hyperparameters from the previous work. It is potentially a little expensive to do hyperparameter tuning like for every single scenario, so we didn't do that. Yeah, but we try to be as fair as possible. I think we were even like for the fixed time, like, because with fixed time, if we're not careful, we can, I think we took I forget right now. I think we took like the average performance over all the systems and rather like a single fixed time rather than the best fixed time for every scenario. Because then that would really beat everything out of the water. Yeah.
okay,
Yeah.
Yeah. Thank you.